delta and delta to star transformation. So before starting the derivation for the formula for the star to delta and delta to star, so let us see what is the need for the star to delta and delta to star transformation. So when we are already seen the concept of the how to convert the resistance are connected in series into the equivalent one, and resistance are connected into the parallel one into the equivalent one. So sometimes what happens, there may be a complex circuit will exist where we can't apply the series parallel combinations. It is not possible to apply here. So the circuit may appear like this. So where the resistance are connected between the three terminals. So the terminals are something say. So these are node A, and this is some part of the connection will be there, and here the some part of the connection node B, and here the some part of the connection node C will be there. So the value for this resistance between the terminals A and B, we can call it as a RAB. We can call, so RAB is the resistance, and this is nothing but RAC, and this is nothing but the RBC we can call. So this network, it is not possible either the series combination, it is not possible to convert. Why? Because there is a connection is there at the node A, and the connection at the node B, and connection is there at the node C. So it is not possible to either apply the concept of series and the parallel combination. So at that time we can make use of the, so this is a network which is appearing in the form of the delta. So this network we can convert into the form of the star network. So like this here. So we can replace this delta network with the equivalent star network. So between the nodes A, B, and C, like this we can replace here. So since this is a resistance, we can call the resistance of the impedance, we can call it as a RA, and this we can call it as a RB, and this we can call it as a RC, we can call here. So this delta network can be replaced with the star network, or sometimes this is also called as a Y network we are going to call. So afterwards we can apply the concept of the series parallel combination, and we can reduce a complicated network into the simplest one, and we can find out the equivalent resistance between the terminals. Respective terminals we can find out here. So in this section, we'll see the derivation of the star to delta transformation, how to convert the star network given star into the delta network, and the given network delta network into the star network. That means that we are going to express the value for the RA in terms of the delta resistance parameters like RAB, RAC, and RBC. And similarly, we are going to express the delta network parameters in terms of the star network elements you are going to convert. So that is, if you are converting delta to star, we are going to call it as a delta to star conversion. And if you are converting from the star to the delta, we are going to convert as a star to delta network you are going to consider. Now let us see the conversion from the delta to star to delta network. Let us see the conversion here, and later we'll do the remaining part, we'll do it here. So in order to derive the expression, what we are going to assume is that, so I consider the star network here, it has been considered. The star network has been considered here. So this is the star network, and we are going to convert into the form of the delta network. So here we are going to find out the equivalent resistance between the terminals A and B. We're going to find out here. So when you're finding the equivalent resistance between the terminal A and B, so this is the impedance which is called ZA, and this is the impedance which is called ZB, and this is called as a ZC. I'm assuming in terms of the ZA, ZB, ZC, so that it may be the either resistance or it may be the capacitive or inductive reactance we can consider. We can consider. So what we do is, when you are finding the equivalent resistance between the any two nodes between the node A and B, we are going to assume that the node C is open here. Either it is applicable even in case of the star, and even the delta network also the same concept is applicable here. Now let us find out the impedance between the node A and B. So we are going to assume that node C is open circuited here. When it is open circuited, so the impedance in the node B will not come here. So the ZB and ZC is appear in the series connection. That's what it has been this here. So ZA. So here the impedance between the terminals A and B is assumed here. A and B. So this is the ZB and this is the ZC here. A and B is assumed. So the equivalent resistance will be, so since this is open circuited, the resistance impedance ZA and ZB are connected in series. So we have assumed ZA plus ZB. And if you look into this one between ZA and ZB, so this is open circuited. So ZAC is coming in series with the ZBC, and this is coming parallel with the ZAB. So that is ZAB is in parallel with the ZAC plus ZBC will get here. ZAC plus ZBC, and we know how to convert this one. So it is a product of these two divided by the sum of the impedances. So by taking the product, we got this expression. So let us call this as equation number one. One will call here. So we find the impedance between the node A and B we find here, and we got this one. So similarly, let us find out the impedance between the node B and C. Let us find out here. That is a node B and C. We are going to assume node A is open circuited. So it is ZB plus ZC will get here. And here between the node B and node C. So here node A we're going to assume as an open circuit. So ZAC and ZAB will come in series parallel with the ZBC. So that is the what we are considered. And by simplifying, we got the same set of expressions we got here. The same set of expressions we got here. And similarly, the denominator remains constant, only the numerator is going to change. And similarly, we are going to find the impedance between the node A and C, we are going to find out. So between the node A and node C, so node A and C will come in series, and ZB is assumed as open circuited. So between the node A and C, so it is ZAC and ZBC is in series. Sorry, between node A and C, ZAC is in parallel with the ZPC and ZAB. So that's what it has been considered here. ZAC is in parallel with the ZAB plus ZBC, and this is the equivalent one we got here. And we assume that equation number 3, equation 1, 2, 3 we got here. Now let us perform the conversion from delta to star or the star to delta transformation. So what we'll do is, in order to find the expression, we are going to take the difference of the equation 1 and 2 we'll take here, because we need the expression for the one terminal we need here. So when you take the difference of the equation 1 and 2, so here we have ZA and ZB is a ZA plus ZB is a. So we'll take the difference of the equation 1 and 2 we'll take here. So that is ZA plus ZB minus ZC minus ZB will get. So ZC, ZB and ZB will get cancelled. So these two will get cancelled. The remaining quantity is this is the ZA. So it is ZA minus ZC. And in the denominator, it's a sum of all the resistances there. We can denote that as a summation ZAB. We can denote that summation is nothing but ZAB plus ZBC plus ZC. And since the denominator is common, we can take that terms here. So here, the terms that is going to get cancelled is, so ZAB and ZBC will get cancelled. So this will get cancelled with the this one. The remaining terms is ZAB, ZAC minus ZBC and ZAC will get, call this as equation number 4 here. And similarly, we'll add the equation number 3 and 4 will add here. So this is equation number 4 and this is equation number 3. If you're going to add, so some of the terms will get cancelled. So if you're going to add, what we'll get is, so ZA, ZC, ZA minus ZC, so ZC will get cancelled, and these are the terms we'll get here. And here we can cancel out the some of the terms will be getting cancelled. That is ZAC, ZAB is ZAC, so and ZBC and ZAC is there. So these are terms will get cancelled. So the resultant will be the ZA is equal to 2ZA is equal to ZAC plus ZAB, ZAC plus ZAB. These two will be there. So these two terms will get cancelled. So this is ZAB and ZAC will be there. Two times will get divided by the denominator will get. So since two are there, so we got the expression for the ZA we got here. That is, we converted the ZA of the delta network. Star network can be replaced with the delta network parameters like this here. So that is, let us go back and let us look into that one. We can express the ZA in terms of the ZAC, ZAB and ZBC we can express here. That is, ZA is equal to the, it's a product of ZAC into ZBC divided by the sum of all the resistances here. That's what it has been mentioned in the, we obtained in the derivation here. So similarly, we can obtain the expression for the ZB we can obtain here. So ZB is equal to the ZAB into ZBC divided by ZAB. That is, it's a product of the two neighbor resistances. That is, are the neighbor impedances like this. So this is ZB is nothing but it's a product of the. So if you write the delta network here, inside the delta network, if you write the star, we'll get like this. So this is the, so this is ZA, and this is ZB will get here. So this is the, it's a node C and this is a node B. This is a node B. So we get, this is a node B. So this is nothing but it's a ZC, and this is nothing but it's a ZB. So we can write ZB is the product of ZAB into ZBC divided by sum of all those things. So similarly, ZC is the product of the neighbor impedances ZAC and ZBC divided by all the resistances. So all the impedances. So we got the same expression we got here. So this is, let us call the expressions as ZA, ZC. We got like this here. We converted the delta network into the star network. We express the star network values in terms of the delta network like this we express it here. So this is how we can convert the given delta network into the star network we can do express. This is called as the delta to star transformation. So similarly, we can do convert. Similarly, we can the star network into the delta network. We can do convert here. So let us consider the conversion of the delta star to delta network here. So what we will be given, the star network will be given. We need to convert in terms of the delta network. Let us do that one. So in order to do this one, so we have the equation number 5, 6, and 7 is there. Let us multiply equation 5 and 6. So ZAB into ZBC. So we get this one, and we'll get the expression. And similarly, we are going to multiply the equation number 6 and 7. And similarly, we are going to multiply equation 5 and 6. 5 and 7, we got like this. Now we are going to add the equations here, and the term of the sum of the terms will be there. So we are going to substitute these terms. We are going to substitute as equal to the value for the it has been considered as a ZC. We can consider here. So if you do substitute here, we get the value for the ZAB and ZBC and ZAC we will get here. So to summarize, if you take the LCM, it will become equal to the ZAB into ZBC plus ZAB into ZA into ZB plus ZBA into ZC plus ZC will get here. So what we'll get is the equivalent values can be expressed here as. So here the given the ZA is there. So ZA can be taken as a we converted the delta to star here. Now in order to convert the star to delta. So if the star network is given, this star network is given, we need to convert in terms of the delta. So what we can do is, so ZA is the thing, but so ZAC we need to find out from the ZAC and the ZB. So ZAC is the thing, but it's a product of the ZA into ZB plus ZB into ZC plus ZC into ZA divided by the opposite to that one is the thing, but the ZB we can write here. Okay, so similarly we can write the ZB we can find out here. So ZB is the thing, but the impedance the ZBC. If I want to find out the ZBC, so it's a product of the ZA into ZB plus ZB into ZC plus ZC into ZA divided by the opposite to that one is ZA is the opposite one. So like we convert the given star into the delta and delta to the star network, we can do convert, and these are the set of formulas represented in the equation number 5, 6, 7, and it is represented in the equation number 8, 9, 10, which is being represented. So in the next session, let us look into the